So here we talk about the classical Chinese remainder theorem. So this theorem is used in number theory. So say we have a problem like this. So x is equivalent to a modulo n1 and x is also equivalent to b modulo n2, where this n1 and n2 are relatively prime to each other. So then there is a solution x which is unique modulo n1 n2. So this we can understand with an example. So say x is equal to 2 modulo 3. So a is 2 and n1 is 3, and also given to us is x is equal to 3 modulo 4. So b is 3 and n2 is 4. So you can see 3 and 4 are relatively prime. So then we can solve the system of equations, and the solution is 11 modulo 12, which is n1 times n2, and this 11 as a solution is unique. So let us first understand how did we get this 11. So for this we will go through the proof of Chinese remainder theorem, which we showed in the last lecture. So this is the solution. So first you have your standard map, your z over n1 n2 z to this map here. So e modulo n1 n2, this natural map goes to e mod n1 and e mod n2. So there's nothing special about this. The inverse image of this map is what is going to give us this solution x right here. Now since n1 and n2 are relatively prime, so there are some integers c and d such that cn1 plus dn2 is 1. So you can say the greatest common divisor of n1 and n2 is 1. So therefore you have this equation. Now you reduce this equation modulo n2. So this term will go away. You have cn1 equals to 1. And then you modulo this equation n1. So this term will go away. So you have dn2 equivalent to 1 modulo n1. So we have this here and this here. So now given these two, we can construct our solution. So solution would be theta inverse of some AB. So A and B are here. So theta inverse is precisely what is going to give us our x, the solution. And this x we give as ADN2 plus BCN1 mod N1 N2. And we can see that this actually satisfies both these equations. So you take x modulo out n1. So you do modulo n1. So this term will go away. And you have a dn2. But dn2 modulo n1 is 1. So this is just 1. So you get this is equivalent to a. So what we have done here is we have taken x modulo n1 is a. Similarly, we want to find x modulo n2. So this is our x. So if you modulo n2, this term will go away to 0. You have bcn1 left, but this out of this bcn1, the cn1 is 1. You can see cn1 is 1 modulo n2. So this becomes 1, and you get x modulo n2 as b. So x modulo n2 as b, and this was our x, adn2 plus bcn1. So let us see this in context of this example. So first step is we have to find c and d so that this equation is satisfied. That is cn1 plus dn2 is 1. So for this you can set c as -1 and d as +1. So if c is -1 and d is +1, you get 1. And our solution is, we said this is our solution, ADN2 BCN1. So ADN2 BCN1 modulo n1 and n2. So modulo n1 and 2 is 12, comes here. A is 2, you can see A is 2, D is 1, we just computed D is 1 here. So we have plugged in C and D so as to satisfy our equation. N1 is given to us as 3, N2 is given to us as 4. So ADN2 is there. Now similarly BCN1, B is 3, C we solved -1 here, and N1 is given to us as 3. So this is it. You plug this in, 8 minus 9 gives you -1. Modulo 12 is equivalent to 11 modulo 12. So this is the answer we were looking for. So we got this answer. So we can extend this to, rather than just two equations here, we can extend it to a bunch of equations. And let us see its more general form. So the general theorem which we will prove is this. So assume you have a bunch of positive integers m1, m2, m3 all the way to mr. So these are positive integers and they're relatively prime in pairs. So greatest common divisor of mi and mk is 1 if I is not equal to k. So pick any two of them, they will be prime to each other. So let b1 to br be some arbitrary integers, and you have system of congruences. So here we just had two congruences, here you have a bunch of system of congruences. So this is a system of congruences, and this system will have a solution x, and it will have exactly one solution modulo the product m1 to mr. So modulo the product of all this. So here we had one solution modulo product of n1 and n2. Here we have again one solution, but now modulo the product of all these r equations. So the proof is, first you set capital M as the product of m1, m2, m3 all the way to mr, and you set mk as m divided by mk. So it has all these it has m1 times m2 all the way to mk minus 1, then mk is skipped because you cancelled it out, then mk plus 1 all the way to mr. So have all the factors except mk. So has all the factors here except mk. So therefore greatest common divisor of mk and this small mk is 1, because capital mk has everything except this small mk because you have divided it out. So therefore greatest common divisor here is just 1, because all these are relatively prime to each other. So mk is relatively prime to every other m here. So therefore you can use this formula here, mk nk plus mk dk is 1. So you can find some integers nk and dk so that this is equal to 1. So now if you modulo out with mk, you get, so you modulo out this small mk, this is what we will get. This is equivalent to 1. So this is our solution which we set. So our solution here, this x we set as b1 m1 n1 plus b2 m2 n2 plus b3 m3 n3 all the way to br mr nr. So this m1 m2 all the way to mr is given to us, so we can construct these m1 m2 m3 all the way to mr. You just take m and keep dividing by small m1, you get capital M1. You divide this by small m2, you get capital M2. b1 b2 all the way to br are also given to us, and n1 n2 n3 all the way to nr you can compute from this equation. So you have mk nk is equal to 1 modulo mk. So this small mk is given to us right here, and this capital mk you obtain from this capital M divided by this. So you can also compute this. So you can compute this, put it here, and you get your x as solution. Now we just check if this x is the correct solution. So notice that mi is equivalent to 0 modulo mk, because the only thing missing from here is small mi. All other factors are in there. In particular mk is a factor in here. So because from here to get to here you have to divide by small mi. So this is 0 modulo small mk if I is not equal to k. So now you do this equation and you modulo it with mk. So the only thing which will remain is bk, mk, nk, and every other thing will be 0 because of this. This is equivalent to 0 mk for I not equal to k. So only the kth part is remaining. But for kth part, you know this is 1. So this is just 1. So this is equivalent to bk modulo this for each k. And so this is the x. So this you can say x is equal to bk modulo mk. So each such equation is satisfied. So x satisfies each such congruence in the system. Now this is also a unique solution, because if there's another x prime which satisfies all these equations, so that is x is equivalent to x prime modulo mk for each k, and since each of them are relatively prime, therefore we will also have x is equivalent to x prime modulo m, because m is just product of all these factors and each of them are relatively prime to each other. So this is the classical Chinese remainder theorem, which is used in number theory to solve such congruences.